Welcome to DAR Tutors. Today we're focusing on IB chemistry higher level, specifically on electron transfer reactions. These reactions are fundamental to chemistry and are often called redox reactions. Our guiding question today is, what happens when electrons are transferred between chemical species? By the end of this session, you should be able to deduce oxidation states, identify oxidized and reduced species and agents, write and balance half equations, and solve problems related to redox titrations. We will provide clear, concept-driven explanations and work through several IB-style examples to solidify your understanding. Let's begin. We'll start with the foundational concepts of oxidation and reduction. Historically, these terms were defined in terms of oxygen and hydrogen transfer. Oxidation was the gain of oxygen or loss of hydrogen, while reduction was the opposite, the loss of oxygen or gain of hydrogen. Let's look at an example. When magnesium burns in oxygen to form magnesium oxide, we can say that magnesium has been oxidized because it has gained oxygen. The equation is 2-O solid plus O2 gas gives 2-O solid. The magnesium gains oxygen, so it is oxidized. Now consider the reaction between copper-2 oxide and hydrogen. Here, copper-2 oxide, or CuO, reacts with hydrogen H2 to form copper and water. In this reaction, the copper-2 oxide loses oxygen to form copper, so it is reduced. At the same time, the hydrogen gains oxygen to form water, so it is oxidized. This is a classic example of a redox reaction, where oxidation and reduction occur simultaneously. One substance cannot be oxidized without another being reduced. While the oxygen and hydrogen definitions are useful in some cases, they don't cover all reactions that are fundamentally similar. To address this, a more universal definition based on electrons was developed. Oxidation is now defined as the loss of electrons. A mnemonic to remember this is OIL, for oxidation is loss. Conversely, reduction is the gain of electrons. The mnemonic RIG helps us recall this. Reduction is gain. This definition includes the historical ones. Let's revisit our magnesium example through this new lens. In the formation of magnesium oxide, the magnesium atom loses 2 electrons to form a magnesium ion, Mg2+. This process is an oxidation. Each magnesium atom is oxidized, forming an Mg2+ ion. We can write this as a half equation. Mg gives Mg2+ plus 2 electrons. The oxygen molecule, O2, gains electrons to form oxide ions, O2. This is a reduction. For every O2 molecule, 2 oxygen atoms are formed, requiring a total of 4 electrons. To get the overall reaction, we combine these half equations. The number of electrons lost must equal the number of electrons gained. The oxidation half equation must be multiplied by 2. Multiplying the oxidation half equation by 2 gives us 2 milliliters, gives 2 Mg2+ plus 4 electrons. Now, adding the balanced half equations and canceling the electrons gives us 2 Mg plus O2 plus 4 electrons, gives 2 Mg2 plus O2 plus 4 electrons. Simplifying by canceling the electrons on both sides, we get the net ionic equation, which represents the formation of magnesium oxide. This electron-based definition is more powerful as it can be applied to any redox reaction, whether it involves oxygen, hydrogen, or neither. Even the electron transfer definition has some limitations, especially in reactions involving covalent compounds where electrons are shared, not fully transferred. For this reason, a third most comprehensive definition was established. This definition uses the concept of oxidation states, sometimes called oxidation numbers. Oxidation is now defined as an increase in oxidation state, and reduction is a decrease in oxidation state. Let's repeat that for clarity. Oxidation is an increase in oxidation state, and reduction is a decrease in oxidation state. To apply this, we need to know how to assign oxidation states using a set of rules. Rule 1. An uncombined element has an oxidation state of 0. Rule 2. The oxidation state of a monatomic ion is equal to its charge. Rule 3. Fluorine always has an oxidation state of -1 in its compounds. Rule 4. Oxygen almost always has an oxidation state of -2, except in peroxides like H2O2 where it's -1, and in compounds with fluorine where it can be positive. Rule 5. Hydrogen almost always has an oxidation state of +1, except in metal hydrides like NaH where it's -1. Rule 6. For a neutral compound, the sum of all oxidation states must be 0. For a polyatomic ion, the sum must equal the ion's overall charge. Let's work through an example. We will deduce the oxidation state of manganese in the permanganate ion, MnO4. The formula is MnO4-. The first step is to recognize that this is a polyatomic ion, so the sum of the oxidation states must be -1. The next step is to assign the known oxidation states. Hydrogen and oxygen are our common elements. There's no hydrogen, so we look at oxygen. Oxygen is not in a peroxide, so we assign it an oxidation state of -2. Now we can write an equation. Let X be the oxidation state of manganese. The equation will be X plus 4 times -2 equals -1. Solving for X, we get X minus 8 equals -1, so X equals +7. The oxidation state of manganese in the permanganate ion is +7. This is a crucial skill for analyzing redox reactions. Now we can use this to identify redox reactions. An increase in oxidation state is oxidation, and a decrease is reduction. Consider the reaction between hydrogen sulfide, H2S, and sulfur dioxide, SO2. The reactants are hydrogen sulfide and sulfur dioxide. The products are sulfur and water. Let's find the oxidation states for each element on both sides of the equation. We'll start with the reactants. In hydrogen sulfide, hydrogen is +1, so 2 hydrogens are +2. This makes sulfur -2. In sulfur dioxide, oxygen is -2, so 2 oxygens are -4. This makes sulfur +4. Now for the products. Sulfur is an uncombined element, so its oxidation state is 0. In water, oxygen is -2, and 2 hydrogens are +2. Let's see what happened to the sulfur atoms. The sulfur in H2S started at -2 and ended at 0. This is an increase, so it was oxidized. The sulfur in SO2 started at +4 and ended at 0. This is a decrease, so it was reduced. Since the sulfur in H2S was oxidized, H2S is the reducing agent. It caused the SO2 to be reduced. The sulfur in SO2 was reduced, so SO2 is the oxidizing agent. It caused the H2S to be oxidized. So H2S is the reducing agent, and SO2 is the oxidizing agent. This reaction is also a special type called a comproportionation. We'll discuss that in a moment. For now, the key takeaway is that by tracking oxidation states, we can identify which species are oxidized and reduced. Let's pause to appreciate the periodic trends that govern redox properties. This can help us predict how elements will behave. As you move from left to right across a period, for example, period 3, you see a trend from strong reducing agents to strong oxidizing agents. Sodium and magnesium on the left are metals. They have a tendency to lose electrons easily, so they are strong reducing agents. Chlorine and argon on the right are nonmetals. Chlorine readily gains electrons, making it a strong oxidizing agent. Argon is inert, so it has no redox properties. This trend can be explained by atomic properties. Ease of oxidation correlates with low ionization energy, and ease of reduction correlates with high electron affinity. These trends are directly related to the position of the elements on the periodic table. Now let's examine a common misconception about redox reactions. There is a common mistake in thinking that a single element cannot be both oxidized and reduced in a redox reaction. This is not always true. The fact is, a single element can be both oxidized and reduced, which brings us to 2 important special cases: disproportionation and comproportionation. A disproportionation reaction is one where a compound containing an element in an intermediate oxidation state is simultaneously oxidized and reduced to form products with higher and lower oxidation states. A classic example is the decomposition of hydrogen peroxide. In hydrogen peroxide, H2O2, the oxidation state of oxygen is -1. It is an intermediate state between 0 in elemental oxygen and -2 in water. In this reaction, the oxygen in H2O2 is reduced to -2 in water and simultaneously oxidized to 0 in O2. So, oxygen has disproportionated. Comproportionation is the reverse process. An element in a higher oxidation state reacts with the same element in a lower oxidation state to form an intermediate oxidation state. We saw this earlier. The sulfur from H2S, OS2, and the sulfur from SO2, OS plus 4, reacted to form elemental sulfur, OS0, which is the intermediate state. Remember, one element can do both. A key application of these principles is in redox titrations, an important experimental technique. A redox titration is a quantitative method to determine the concentration of an unknown oxidizing or reducing agent. The process involves reacting a solution of known concentration, called the titrant, with a solution of unknown concentration, the analyte, until the reaction is complete. We use a burette to add the titrant to a flask containing the analyte. The endpoint is usually detected by a sharp color change, either from the reactants themselves or by using a redox indicator. The most common oxidizing agent used in titrations is potassium manganate, Kernov. The manganate 7 ion, MnO4- is a deep purple color. In an acidic solution, it is reduced to the manganese T2 ion, Mn2+, which is nearly colorless. This distinct color change makes it self-indicating, meaning you often don't need a separate indicator. A note of caution? Manganate 7 titrations must be acidified with sulfuric acid. If you use hydrochloric acid, the permanganate will also react with the chloride ions, leading to inaccurate results. It's time for our call to action. If you're finding this content helpful, we encourage you to contact our tutors for personalized expert tuition in IB, A-Level, and IGCSE. Our tutors can provide tailored support to help you master challenging topics like this one. Now let's continue with our worked examples to build your problem-solving skills. Our first worked example involves a redox titration to find the percentage of sodium nitrate 3 in a sample. This is an IB-style problem. The problem states that a 100 gram sample containing NaNO2 is dissolved and titrated with 0.01 molar potassium permanganate solution. The titration required 12.115 cubic centimeters of the KMNO4 solution. We are also given the key half equation for the oxidation. The nitrite ion NO2 is oxidized to the nitrate ion NO3. Our first goal is to calculate the percentage by mass of NaNO2 in the original sample. We will follow a structured approach to solve this. First, we need to balance the oxidation half equation. NO2 becomes NO3. To balance the oxygen atoms, we add one water molecule, H2O, to the left side. Then, to balance the hydrogen atoms, we add two hydrogen ions, 2H+, to the right side. Finally, to balance the charge, the left side has a charge of -1 and the right side has +1. We add two electrons to the right side to get a balanced half equation. NO2 plus H2O gives NO3 plus 2H plus 2 electrons. The reduction half equation for MnO4 is a standard one we should know. It is MnA4 plus 8H plus 5 electrons gives Mn2 plus 4H2. Next, we combine these half equations to get the overall redox equation. We need to make the number of electrons equal. The least common multiple of 2 and 5 is 10. So we multiply the oxidation half equation by 5 and the reduction half equation by 2. This gives us 5 moles of nitrite ions reacting with 2 moles of manganate ions. Now that we have the balanced equation, we can use the titration data to calculate the percentage of NaNO2 in the sample. This is a classic quantitative problem that will always follow these steps. First, find the moles of the titrant, which is KMNO4. Moles equals concentration times volume. The concentration is 0.0100 mol per dm3, and the volume is 12.15 cubic centimeters, which is 0.01215 dm3. This gives us 0.01215 moles of MnO4. Next, use the stoichiometry from the balanced equation to find the moles of the analyte. NaNO2. The mole ratio is 5 moles of NO2 for every 2 moles of MnO4. So, moles of NO2 equals 5 to 2 times the moles of MnO4, which gives us 3.0375 times 10 to the power of -4 moles. Now, we convert these moles to mass. Mass equals moles times molar mass. The molar mass of NaNO2 is 6,900 grams per mole. This gives us a mass of approximately 0.0296 grams of NaNO2 in the sample. Finally, we calculate the percentage. Percentage equals the mass of the substance divided by the total sample mass times 100. The result is 2.095875%. Following the significant figure rules, we round our final answer to 2 significant figures. giving us 2.1%. So the sample contains 2.1% sodium nitrate 3 by mass. Here is our second worked example. This time, we are asked to determine the value of X, which represents the number of water molecules of crystallization in a hydrated iron 2 sulfate salt. In this problem, 1.25 grams of the hydrated salt are dissolved, and a 2500 3 portion of the resulting solution is titrated with 0.12 molar potassium dichromate solution. The titration required exactly 17.50 cm3 of the dichromate solution. The key to solving this is the balanced net ionic equation, which is provided. The dichromate ion, Cr2O72, oxidizes the iron 2 ions, Fe2+, to iron 3 ions, Fe3+. In this reaction, 1 mole of dichromate oxidizes 6 moles of iron 2. Notice that the mole ratio of dichromate to iron 2 is 1 to 6. Keep this in mind as we proceed. Our first step is to calculate the moles of the titrant used. The volume of dichromate solution used was 17.50 cubic centimeters, or 0.0105 cubic decimeters. The concentration was 0.120 moles per radium-3. Multiplying these gives us 0.22 moles of dichromate ions. Now we use the stoichiometry to find the moles of iron 2 ions that reacted. Since the mole ratio is 1 to 6, the moles of iron 2 ions must be 6 times the moles of dichromate. So 6 times 0.0210 moles gives us 0.01126 moles of iron 2 ions in the 2500 cm3 aliquot. We're not done yet. The value of X relates to the moles of water in the original sample. We've only calculated the moles of Fe2+ in a small portion of the solution. So the next step is to scale up our result to the entire sample. The original solution was made up to 250 cubic centimeters, and we took a 25 cubic centimeter aliquot for titration. The aliquot is 1/10 of the total volume. Therefore, the total moles of Fe2+ in the entire 250 cm3 sample is 0.10126 moles times 10, which is 0.126 moles. Now we have the total moles of iron 2 sulfate in the sample. This is the same as the total moles of the hydrated salt. The total mass of the hydrated salt in the sample was 1.25 grams. Mass equals moles times molar mass. So 1.25 grams equals 0.126 moles times the molar mass of the hydrated salt. Solving for the molar mass, we get approximately 9.92 grams per mole. But this molar mass is far too low. What went wrong? Let's reread the problem carefully. I see. The original sample mass was actually 1.25 grams, but it was dissolved in 250 cubic centimeters of water, not 500 cubic centimeters. Let's correct our calculation with the correct volume. The total volume was 250 cm3, not 500, so the aliquot of 25 cm3 was 1/10 of the total. Our calculation of 0.126 moles is correct, and the original sample mass was 1.25 grams. So, molar mass of the hydrated salt is 1.25 divided by 0.126, which is approximately 9.92 grams per mole. Still incorrect. Let's look at the provided solution in the notes. The example in the notes starts with a sample size of 1 gram and a total volume of 500 cubic centimeters. It seems the problem I just wrote down was a variation on that. Let's use the exact numbers from the notes. A 101.2 gram sample is dissolved in 500 cubic centimeters of water. A 2000 cubic centimeter aliquot is titrated with 0.100 molar dichromate, requiring 2400 cubic centimeters. Let's follow this through the calculation. Okay, let's restart the second worked example using the precise figures from the notes. This is a very common type of IB problem, so let's get it right. The problem is to determine the value of X in FeSO4 XH2O using the titration of the iron 2 with dichromate. We have 101.2 grams of the salt dissolved in 500 cubic centimeters of water. We titrate 20.100 cubic centimeters of this solution with 2400 cubic centimeters of 0.100 molar dichromate. The balanced equation is the same. The mole ratio of dichromate to iron 2 is 1 to 6. First, calculate the moles of dichromate used. Concentration times volume gives us 0.00240 moles. Second, calculate the moles of iron 2 ions in the aliquot. Using the 1:6 ratio, we get 6 times 0.0240, which is 0.4114 moles. Third, scale up to the total volume. 20 cubic centimeters is 1/25 of the 500 cubic centimeter total. So total moles is 25 times 0.01144, which equals 0.360 moles. This is the total moles of FeSO4 in the 101.2 gram sample. Fourth, we find the moles of water. The moles of the hydrated salt is also 0.360 moles. The moles of pure FeSO4 has a mass of 0.360 moles times 151.91 grams per mole, which is 54.7 grams. The difference between the total mass of the hydrated salt and the mass of the anhydrous salt is the mass of the water. 101.2 minus 54.7 is 46.5 grams of water. Fifth, we convert this mass of water to moles. 46.5 grams divided by the molar mass of water, 18.02 grams per mole, gives us 2.58 moles of water. Finally, we find the mole ratio of water to FeSO4 to get X. Moles of water, 2.58, divided by moles of FeSO4, 0.360, gives us approximately 7.16. Since X must be an integer, we round to the nearest whole number. Therefore, X is 7. The formula of the hydrated salt is FeS4.7H2O. That was a much more rigorous problem, illustrating the power of redox titrations to determine an unknown quantity. Let's work through one final, more complex example. A back titration. This is a common technique used when the reaction is too slow, the analyte is volatile, or an excess of reactant is needed. The problem asks for the concentration of sulfur dioxide, SO2, in a sample of white wine. A 50.0 cubic centimeter sample of wine is reacted with an excess of 0.01 molar iodine solution. The unreacted iodine is then titrated with 0.02 molar sodium thiosulfate solution, requiring 23.60 cubic centimeters to reach the endpoint. We need to find the concentration of SO2 in the original wine. A back titration involves two reactions. The first reaction consumes the analyte, SO2, and part of the excess reactant, I2. The second reaction determines how much excess reactant, I2, is left over. The first reaction is between sulfur dioxide and iodine. The second is the titration of the remaining iodine with thiosulfate. We are given the equations for both reactions. The overall strategy is, find the total moles of iodine added. Find the moles of iodine that reacted in the back titration, this is the excess. Subtract the excess from the total to find the moles of iodine that reacted with the SO2, and then use that to find the moles and concentration of SO2. Let's execute the strategy we just outlined for the back titration problem. First, we'll calculate the total moles of iodine that were added to the wine sample at the beginning of the experiment. Moles equals concentration times volume. We added 40.0 cubic centimeters, or 0.0400 dm3, of 0.01 molar iodine. This gives us a total of 0.0400 moles of iodine. Second, we'll use the second reaction to find the moles of thiosulfate used in the titration. The volume was 23.60 cubic centimeters, or 0.02360 dm3, and the concentration was 0.02 molar. This means 0.0472 moles of thiosulfate were used. Third, we'll use the stoichiometry of reaction 2 to find the moles of excess iodine. The mole ratio of I2 to thiosulfate is 1:2. So, the moles of excess iodine is half the moles of thiosulfate, which is 0.0236 moles. Fourth, we find the moles of iodine that actually reacted with the sulfur dioxide. This is the difference between the total iodine added and the excess iodine we found. 0.0400 total moles minus 0.036 moles excess gives us 0.0164 moles of iodine that reacted with the SO2. Fifth, we use the stoichiometry of reaction 1 to find the moles of sulfur dioxide. The ratio is 1:1. So the moles of SO2 in the 50.0 cubic centimeter sample of wine is also 0.000164 moles. Finally, we calculate the concentration of sulfur dioxide in the wine. Concentration equals moles divided by volume. The moles of SO2, 0.0164, divided by the volume of wine, 0.0500 dm3, gives us a concentration of 0.00328 moles per dm3. This complex back titration allows us to precisely determine the concentration of sulfur dioxide, a key preservative in the wine. Let's quickly review the key takeaways from this session. We learned that oxidation and reduction are electron transfer processes, which we can track using oxidation states. An increase in oxidation state is oxidation, and a decrease is reduction. We also saw how to apply this in practice by balancing half equations and solving quantitative titration problems, including the more advanced technique of back titration. Finally, we explored the periodic trends in redox properties, linking an element's position on the periodic table to its tendency to lose or gain electrons. This forms a solid foundation for understanding many important chemical and biological processes. Mastering these concepts is essential for success in HL chemistry. Now, let's put your knowledge to the test with some IB-style practice questions. Question 1 asks you to deduce the oxidation state of oxygen in OF2. Pause the video and try to solve it. And here is the solution. Fluorine is the most electronegative element, so it always takes an oxidation state of -1. In OF2, there are 2 fluorines for a total of -2. The compound must be neutral, so oxygen's oxidation state must be +2. This is an exception to the rule that oxygen is usually -2. Question 2 asks you to balance the half equation for the oxidation of chloride ions to chlorate I ions in an alkaline medium. This is a common challenge for IB students. Let's work through the solution step by step. First, balance the atoms other than oxygen and hydrogen, which are already balanced. Second, balance oxygen. The left side has none, the right has one, so we add 1 water molecule to the left. Third, balance hydrogen. The left side has 2, the right has none, so we add 2 H+ ions to the right. This gives us ClC plus H2O gives ClO plus 2H+. Fourth, we balance the charge with electrons. The left has a charge of -1, and the right has a charge of +1. We add 2 electrons to the right to balance it. This is the balanced half equation for an acidic medium. Finally, we convert it to alkaline medium. We add 1 OH ion to each H+ ion to form water. On the right, 2H+ plus 2OH becomes 2H2O. On the left, we add 2OH. We can cancel 1 water molecule from each side. The final balanced half equation for alkaline conditions is Cl plus 2OH, gives ClO plus H2O plus 2 electrons. Let's continue with the practice questions. Question 3 is a multi-part question focusing on identifying redox species and their roles. The reaction is between magnesium metal and aqueous copper 2 nitrate. First, write the net ionic equation. Second, state which species is reduced. And third, identify the oxidizing agent. Let's tackle each part. To find the net ionic equation, we first write the full ionic equation. Magnesium is solid, so it stays. Copper nitrate is aqueous, so it dissociates into copper 2 ions and nitrate ions. The products also dissociate. We can see that nitrate ions appear on both sides as spectator ions, so we cancel them. The net ionic equation is Mg solid plus Q2 plus aqueous gives Mg2 plus aqueous plus Q solid. For part B, we need to find the species that is reduced. Reduction is a decrease in oxidation state. Magnesium goes from 0 to +2, so it's oxidized. Copper goes from +2 to 0, which is a decrease. So copper 2 ions, or Cu2+, are reduced. For part C, the oxidizing agent is the species that causes the oxidation of another, so it gets reduced itself. The oxidizing agent is the species that is reduced. Since Cu2+ was reduced, it is the oxidizing agent. Our next question is about redox indicators. Why is phenolphthalein an unsuitable indicator for a redox titration? The answer is straightforward. Phenolphthalein is an acid-base indicator. It changes color based on pH, not on oxidation state or electron transfer. It cannot tell you when the stoichiometric amount of reactants have reacted in a redox reaction because its color change is not linked to the redox process itself. We have one more practice question. This one is a conceptual question about periodic trends. Question 5 asks you to state and explain the trend in the oxidizing strength of the halogens in aqueous solution as you move down the group from fluorine to iodine. The trend is that oxidizing strength decreases as you go down group 17. Fluorine is the strongest oxidizing agent, and iodine is the weakest. Now, let's explain this trend at the atomic level. An oxidizing agent is a substance that is reduced. The halogens are nonmetals that are reduced by gaining one electron. They become a halide ion, Xe. Down the group, the atoms have more occupied energy levels, making them larger. There is also increased electron shielding from the inner electron shells. This combination means the attraction between the nucleus and a potential incoming electron is weaker. Therefore, the elements further down the group are less able to attract and gain an electron, and their tendency to be reduced decreases. This makes them weaker oxidizing agents. Fluorine, being small and having little shielding, has the strongest attraction and is the most powerful oxidizing agent. This concludes our session on electron transfer reactions. I hope this detailed explanation and worked examples have clarified this essential topic. Thank you for watching. Finally, we have one last problem that combines both stoichiometry and redox titrations, as is common in the IBHL exam. This question requires a multi-step calculation. Pause the video and give it a try. Here is the problem. An unknown potassium manganate 7 solution is reacted with potassium iodide, Ki. This is a primary reaction that liberates iodine. Then, the iodine liberated is titrated with sodium thiosulfate solution to find the initial concentration of the manganate 7. We will solve this by starting at the end of the titration and working our way backwards to find the concentration of the permanganate. Step 1. Calculate the moles of thiosulfate used in the titration. The volume was 2620 cnm3, or 0.02620 dm3, and the concentration was 0.500 mol dm3. Multiplying them gives 0.0131 moles of thiosulfate. Step 2. Calculate the moles of iodine liberated. We use the stoichiometry of reaction 2, where the mole ratio of iodine to thiosulfate is 1 to 2. So, the moles of iodine is half the moles of thiosulfate. 0.131 divided by 2 gives 0.00655 moles of iodine. Step 3. Calculate the moles of permanganate in the aliquot. We use the stoichiometry of reaction 1. The mole ratio of permanganate to iodine is 2 to 5. The moles of permanganate is 5 times the moles of iodine. So, 0.00655 times 5 gives us 0.00262 moles of permanganate in the 2500 cnm3 aliquot. Step 4. Calculate the concentration of the potassium manganate solution. Concentration equals moles divided by volume. We found 0.0262 moles of permanganate in a 2500 cnm3 aliquot. Converting the volume to dm3 gives 0.02500 dm3. Dividing these gives a concentration of 0.148 moles per dm3. Looking back at the data, the concentration of thiosulfate is given to 3 significant figures, 0.500. So, we round our final answer to 3 significant figures as well. The concentration of the potassium manganate at solution is 0.105 moles per dm3. This type of linked calculation is a core skill for the IB exam.